127, it will be stored in the left RAM, and 128 to 255, it will be stored in the right RAM. So once it started completely for the frame 1, then it will read for the 0, 16, 32, 48 of row address for the second stage. So the rows will be freed up. So in this case, when the even frames are there, we'll start writing 0, 1, 2, 3 in the horizontal direction as a frame like this. So instead of 0, 16, 32, just sample 0, sample 1, sample 2, sample 3. Like that, we can start writing here. So it will keep on writing in the row-wise order for the 255 for the even frame. So single set of 16 cross 64 RAM is sufficient to process and to store the FFT stage 1 coefficients. So when we move on to the stage 2 FFT coefficient RAMs, still it get off of the memory. That means only 2 memories we have. The reason is, in the last stage, due to the mirror coefficients in the transformation function, we can avoid the redundant copying of the data and redundant computation of the data. So the last stage, actually we have only 128 or for the 8 kilohertz or 256 for the 512 FFT. So half of the RAM will be required. That's what here 2 memory alone is required. So the master counter will produce all this address from RAM 1 to RAM 35. That means all 35 RAMs, it will produce the address values from the master counter. So after the FFT coefficients, the MEL coefficients, the pre-stored coefficients will be read for the MAC S of n, which actually 2 MAC to compute 2 different bank values. Then whatever the 2 values are there, it will be given to the log of S of n. So this log of S of n will use a single adder, 2 adders. These 2 adders will add the 3 tables from the x1 table, new x2 table, and the q log table. So all these 3 values will be added for the log of S of n, and it will be given to the MAC 3, which is computing the C of k. So to compute Z of k, again we need the cost value. For the cost and cost of x, whatever the address is there, it will be given by the master counter. Similar for this structure, for the 16 kilohertz, the address location, that means address RAM alone is changed. So the architecture is same, only the RAM location or the RAM size is different between 8 and 16. If you observe, each RAM will have 16 cross 128 locations. So the count is exactly double compared to the 8 kilohertz. So what are the namings in the sense? The framing RAMs actually store the framed samples with respect to the window, and the MEL coefficient RAMs will store the non-zero MEL filter bank coefficients. MAC actually for the energy computation, also for the feature vector computation, and FFT stage 1 and stage 2 RAMs are to store the FFT coefficients from the 1-dimensional to the 2-dimensional, and twiddle factor RAMs, which is the intermediate RAM, which is used to compute the FFT for the butterfly, and cos RAM is for the inverse cosine transform for the MEL septal vector, and then address generator, which is a master control unit or else master counter, which actually generates all the address line and all the enable and disable lines. So if you observe this, when I write in the input RAM, I can able to write only 1 RAM. All other RAMs, that means I can able to mostly write only in 2 RAMs. All other RAMs will not have the write provision. So all other RAM write enable should be 0 except the 2. Similarly, when I read, only 4 RAMs will be in the read operation. Remaining 4 will be in the disable mode. Similarly, for the FFT coefficients, 2 RAMs will be for the read and 1 RAM or 4 RAM will be for the write. So similarly, it will keep on go. So all this enable and disable signal also will be generated from the master counter unit. So the clock sequence, if you observe the framing and windowing, the frame once after the reset, the frame 1, frame 2, frame 3, that means the non-overlapped frames alone it's mentioned. That means whatever the frame values are there, it will be mentioned as separately. So frame 1 is a 0 to 199, frame 2 is 80 to 159, 80 to 199 and 0 to 40, and frame 3 is 160 to 199 and 0 to 160 and so on. So if you observe the framing, that means input samples will be written at 0 timing instance, but stage 1 FFT will start operation in middle of the frame 1. That means at 192nd clock cycle for the 8 kilohertz and 384th clock cycle of 16 kilohertz. Similarly, for the stage 2, the F1, F2, whatever the calculation is there, will be shifted to the frame 2 option. So energy coefficient, again it's shifted. So what is the overall latency we have for the entire thing? It is mentioned as a signal flow in this table. If you observe the input RAM, that means it mentioned two things. One is what is the bit size and the clock count. So before going to the clock count, we need to discuss about the bit size for the architecture. So initially the speed sample is 16-bit. So after Windows and framing, we'll get a 16-bit sample. But once we need to compute for the FFT, we need a signed signal. That means whether we have to add or subtract, we'll get both positive and negative values. So one more sign bit will get added. So 17-bit input we have to give with the padded 0 as an initial input. So after FFT computation, that means if it is a 16-point FFT, minimum it has to go for cross for 4 location. So after 4 location, minimum we need to go for a 3 multiplication. After the 3 multiplication, from 16 point, it will go nearly 44 bit value. So, but out of this 44 bit value, we have only 26 bit value as a real part, and the remaining will be the decimal part values. And each coefficient has real component, also the imaginary component. So we can avoid this 27 to 44, or we can able to truncate some of the bits from the 27 to 44. So at last, the entire flow follows maximum 33 bit for the entire flow maximum accuracy. So we restricted everything with the 33 bit resolution with some kind of a floating point representation, which has a magnitude, exponent and sign, but it's not as like conventional IEEE's format. It has a different exponent bit and different mantissa bit in each and every stage. So, but the overall bit we will try to maintain as was 33 alone. So after FFT, the FFT stage 1, FFT stage 2, FFT coefficients, S of n, log of n, cos of x, C of x, k, everything is following 33-bit accuracy for the entire flow. So that's what it's mentioned for the input RAM. It was 16 and the output bit for the input RAM also 16. But the input bit for the FFT S1 is 17, including of the 1-bit sign. And output bit is 33. Similarly for the clock count. So input RAM 0 to 199. This is based on the first frame. So when I start writing the first frame, in each and every stage, in which clock count it is starting the operation. That's what it's mentioned here. So for the input RAM 0 to 199, it was the first frame operation. So the clock count for 16 kilohertz is 0 to 399. So for the 16-point FFT stage 1, it will start operation at 192nd clock cycle, and till 255 it will go, since 64 clock cycle is required to complete the entire FFT computation, and then extra 16 clock cycle for the other control to initialize the values. Similarly for the 16 kilohertz sample, 384 to 511. So for the 16 kilohertz FFT stage 1, so it need a latency of 192. After 192, each and every clock cycle, it will start operation for each and every sample. So for the 16 kilohertz, it need a latency of 383. So 384th clock cycle will start operation. So when we go for a FFT stage 1 RAM, after 192 samples when it read, after 8 clock cycle, it will start giving the other output. So 192 to 8 if you start counting, 199th clock will get the first FFT coefficient. So from 199 to 262, we'll get the FFT coefficient for the first frame in the one-dimensional vector. So similarly for the 16 kilohertz, 399 clock to 512 clock, we'll get the first frame coefficients as a vector. So from FFT stage 1 RAM, if you want to read for the FFT stage 2, as like the FFT stage 1, 192nd sample, which is the 8th sample from the last. So again, for the FFT stage 2, 8th sample from the last, if you check, it will be 255. So 255th clock cycle, we'll get the 8th sample from the last. So 255 to 318 is the operating clock timing for the FFT stage 2. So similarly for the 16 kilohertz, it was 511 to 368. So after completing this FFT stage 2, we need to store the values. Again, it is following for the 8 difference for the FFT stage 2. So 255 plus 8, if you add 262, so 262 to 325, FFT stage 2 will happen. But here it was 16 kilohertz, which has a 16 clock cycle. So if here we need to add 16, so which is actually 526. 526 to 653 is our next time period for the 16 kilohertz. Similarly, for the Mach 1 of S of n, it will go for the 294, which is actually a 64th sample of the S of n. So when, as we said, 0th bank and 60th bank will start operation at same time, which is actually